This module covers material on standardized tests. It will be presented in two parts. Part 1 will cover issues related to measurement error and two related concepts, reliability and validity. Part 2 will cover the types of standardized tests, their limitations, principles related to the use of these measures, and important tips for their administration. Not all published tests are good. However, contrary to what you have heard, not all published tests are bad either. You need to understand reliability and validity so you can make informed decisions about buying and using a test, as well as knowing the extent to which you can use the results to make good interpretations and decisions. You need to be an enlightened consumer. Test publishers provide information from one or several reliability and validity studies to determine that the information produced from the test, usually the scores, are accurate and measure what is intended. They provide statistical estimates of error. There are three concepts within scoring: true score, confidence intervals, and standard error of measurement. All tests have error. There are generally two major types of error: random measurement error and non-random human error that are associated with tests. Let's look at random measurement error first. There are generally two major factors that influence consistency of assessment performance. 1. The content or particular sample of tasks on any form of assessment, and 2. The occasion on which the assessment is administered. Suppose that all of the tasks that might be appropriate for assessing achievement for a particular set of learning targets can be described. This description of possible tasks is called a domain of achievement. For instance, this domain could be all the open-ended tasks that might be used to assess third graders' ability to solve mathematical problems involving simple multiplication. Now suppose you want to determine the percentage of the domain a student knows. Rather than administering the entire domain, which is clearly impossible, you select from the domain a random sample of, say, 10 items or tasks that you believe are representative of the domain, and then you administer them to the student. Clearly, the student's score on this assessment depends on which tasks happen to be included in the sample. A different sample of 10 tasks would be easier or harder than the first sample and would result in a higher or lower score for her. The difference in performance is a result of using a different content sample. Now suppose you administer the first sample of 10 tasks on a bad day for a student, and the same sample on a good day to that same student, resulting in another difference in performance. This would be the result of sampling on a different occasion. It is certainly possible that both content and occasion may work together to influence assessment performance. A student may have been sick the night before and unable to study. A room may be too hot or too crowded, making it difficult to concentrate. In addition to random measurement error, which is expected, non-random human error is harder to predict and to be accounted for. The sources for such error are varied, from more individualized ones, such as using the wrong formula, faulty items, data entry, and poor supervision, to more systematic ones, such as problematic test design, insufficient piloting, and unreliable scores. We can draw several important conclusions from this discussion. Interpreting assessment results of a student obtained on a particular occasion with a particular sample of tasks has definite limitations. Assessment results must be reasonably consistent. Perfect consistency is not possible over different samples of content, tasks, and occasions. There are different kinds of consistencies. Assessment results may be consistent in some ways, but not others. For instance, students' assessment results may not be consistent over repeated assessment on different samples of tasks, but may be very consistent over repeated assessment on the same sample of tasks over a month. As a result, you should know how you want to use the results of repeated assessment so that you can make good interpretations. If your assessment concern is to generalize today's performance to how well that student is likely to perform next month on the same sample of tasks, then consistency over time probably is more relevant to you than information about score consistency over different samples of tasks. On the other hand, if you know the students are learning rapidly and changing constantly, then consistency of scores over time is less relevant. Classical test theory assumes that each person has a true score that would be obtained if there were no errors in measurement. Because instruments used for measurement are imperfect, the score that is observed for each person most times is different from the person's true abilities or characteristics. An approximation of the true score would be obtained if you could give the test an infinite number of times and take an average of all these administrations. Classical test theory states that the difference between the true score and the observed score is the result of errors in measurement, as in the following formula: x equals t plus e, where x is the observed score, t is the true score, and e is error. SEM is also known as standard error. It is the statistical approximation of the variation that occurs between the observed score and the true score for a group on which the test norms are based. It is an estimate of error and represents the average amount of measurement error and is basically interpreted as a standard deviation of all errors in measurement. For the purposes of this course, it is important to keep in mind that the smaller the SEM, the less error there is, and therefore the more reliable the test is. The larger the SEM, the more error there is, and therefore the less reliable the test is. As I keep saying, no test is perfect, and because no test is perfect, we use another important concept to estimate where a child's true score might lie. Confidence intervals, or CI, provide a range of scores within which a child's true score lies. It is based on his or her performance and the standard error of measurement of the test. The formula is CI equals the observed score plus or minus the standard error. For example, if the observed score equals 80 and the standard error of measurement equals 4, then the true score is thought to fall between 76 and 84. So in this example, the confidence interval is determined by adding the SEM to the score obtained on the test and subtracting the SEM from that score. The range you get, 76 to 84, contains the hypothetical true score. Wider confidence intervals suggest a test is less reliable than a narrow confidence interval. We have to realize the fact that concepts such as true score, CI, and SEM are part of a theory about measurement. Like all theories, they are a model of how the world operates, and they are not without error. Consequently, We need to recognize that the child's score is only an estimate of the child's ability and always contains error. We need to keep this in mind when interpreting scores, especially when interpreting scores for parents. We also need to keep this in mind when deciding whether a test is reliable enough to use. As you may have gathered from my comments, reliability is the extent to which a test is repeatable and yields consistent scores. In order to be valid, a test must be reliable, but reliability does not guarantee validity. The goal of estimating reliability is to determine how much of the variability in the test scores is due to measurement error and how much is due to variability in true scores. Reliability can improve by 1. Getting repeated measurements using the same test, and 2. Getting many different measures using slightly different techniques and methods. There are 3 primary types of reliability. The specifics of each are beyond the scope of this course. However, you should understand the fundamental characteristics of each type. They are test-retest, alternate form, and internal consistency. We will discuss each of these separately now. The first way to measure reliability is through the mechanism of test-retest. The same test is given to the same people on 2 occasions. The scores are correlated, and if the reliability coefficient is positive and high, the test is reliable. For norm reference tests, comparison is made between the rank of the person at the time of the first test and the rank of the person at the time of the second test. While for criterion reference test, comparison is made between the score on the first test and the score on the second test. The closer in time of the administrations, the higher the correlation coefficient. However, students may remember the test, rendering the coefficient less meaningful. Another way to measure reliability is using an alternate form. This type of reliability is also known as parallel form or equivalent form reliability. This is where 2 versions of the test are constructed and given to the same people on 2 occasions. Reliability is determined by correlating scores on the 2 forms of the tests. Scores on the 2 forms should show a high positive reliability coefficient. For norm reference test, correlations should be high, while for criterion reference tests, scores should be similar. The time interval between the administrations of the test forms is less important than in test-retest. The third measure of reliability is the internal consistency of the items. This type of reliability looks at how the items of a test correlate with each other. Internal consistency is commonly measured using a statistical technique called Cronbach's alpha, which is based on inter-item correlations. A score between 0 low and 1 high is obtained. The greater the number of similar items, the greater the internal consistency. That's why you sometimes give very long scales, asking a question a variety of different ways. If you add more items, you get a higher Cronbach's. Generally, alpha of 0.80 is considered a reasonable benchmark. Split half reliability is a type of internal consistency. In the split half procedure, the test is divided into 2 halves. For example, the odd number versus the even numbered items. Scores on each half are correlated. If the test is reliable, the score on the 2 halves should show a high positive reliability coefficient. The odd-even split halves procedure is inappropriate when groups of items are linked together, such as when a cluster of items requires an answer based on the same reading selection, or the same data table, figure, or graph, etc., or when items are grouped in homogeneous clusters in a matching exercise. In these cases, you might want to consider splitting the test by sections. Reliability is measured by a reliability coefficient, which expresses the degree of consistency in the measurement of test scores. It represents a correlation between sets of scores from people who have been given the test on 2 occasions. The values for reliability coefficients range from 0 to 1.0. A coefficient of 0 means no reliability, and a 1.0 means perfect reliability. Since all tests have some error, reliability coefficients never reach 1.0. Coefficients between 0.80 and 1.0 are acceptable, but 0.85 or higher are desirable, especially when used with young children. Another topic important to standardized tests is that of validity. In order to be valid, a test must be reliable, but reliability does not guarantee validity. The internal validity of a test is the extent to which it measures what it is supposed to measure. The external validity of a test refers to how well it can be generalized to others in the population for which it was developed. Here is an example to help you better understand the concept of validity. A conceptual definition of aggression could be an act intended to cause harm to another person, but the operational definition might be seeing how many times a child hits a doll, how often a child pushes to the front of a line, how many physical scrapes he or she gets into on the playground. Are these valid measures of aggression? How well does the operational definition match the conceptual definition? As shown in the above example, validity is a subjective judgment made on the basis of experience and empirical indicators. There are 2 major threats to validity. The first comes from the quest for reliability. There is a dangerous trend that in the quest for highly reliable assessment, only the more easily and reliably assessed parts of a construct are assessed. For instance, speaking and listening may be left out of language tests because of reliability issues, and writing may be assessed through multiple choice tests. While reliability is necessary for validity, a highly reliable test may be less valid because it sampled only a small part of the construct, so we cannot make confident generalizations from the results. Sometimes, even if one particular assessment may seem less reliable because it cannot be standardized as precisely as examination marking, it may be a more dependable assessment of the construct being measured. A second threat to validity is witnessed when a test is used for a purpose it was not designed for. While this sounds unlikely in theory, it actually is not uncommon in practice. For instance, if a test is intended to measure reasoning skills, but students can do well on it by rote learning of prepared answers, then it is not doing what it claims it is doing. It therefore lacks validity. This is because success has come from performance irrelevant to the construct being assessed. There are 3 major types of validity: content validity, criterion validity, which is further categorized into 2 subcategories, concurrent validity and predictive validity, and the last major type of validity, construct validity. Content validity refers to the adequacy with which the content of a test represents the content of the assessment domain. For instance, a semester or quarter exam, that only includes content covered during the last 6 weeks is not a valid measure of the course's overall objectives. It has a very low content validity. When the idea of content representation was first dealt with, the focus was dominantly on knowledge. But since then, the notion of content can embrace knowledge, skills, or attitudes. Content, therefore, is thought of in a much broader way. In order to make sure of the representativeness of the test, it is a good idea for the test to be reviewed by content experts. Criterion validity answers the question whether the test results match up with other known measures of a characteristic. There are two types of criterion validity: concurrent and predictive. Concurrent validity refers to the process where a test result is compared with another indicator at the same time, while predictive validity refers to the process where the test result predicts a later outcome. For instance, if the end-of-the-year math tests in 4th grade correlate highly with the statewide math tests, they would have high concurrent validity. If the SAT math scores correlate highly with average math GPAs, the SAT has a highly predictive validity. Construct validity refers to the extent to which a test measures a construct or trait, typically as predicted by some rationale or theory. Does the test produce a result that is in agreement with an established theory? Examples of constructs include intelligence, self-esteem, nonverbal reasoning, or mechanical aptitude. For instance, you can state that a test of intelligence has construct validity if children who obtain high scores on the test have better recall, understanding of concepts, imagination, grades in school than those who have low scores on the test. This concludes Part 1 of the presentation on standardized tests. It has covered scoring, reliability, and validity. Please proceed to Part 2, where you will hear about types of standardized tests, their limitations, principles of testing, and their administration.